Okay, welcome to lecture 5 of the planets. In this lecture, we're going to talk about two topics that are in some ways related as if this were a philosophy class. We're going to talk about some historic scientists from the 1500s and 1600s that really shaped our thinking, not just about the universe, but about our place in the universe, and even more, they shaped our thinking about how we ask questions about nature and how we try to answer those questions and then do experiments to determine if our ideas are right. So we're going to be talking about a few historical astronomers, and I have to tell you confidentially, I'm not a very big fan of history per se. I don't think history in and of itself is interesting, but I am very interested in learning what historical figures have to tell us about how to live our lives now and maybe understand our world now. And we're going to be describing, as an offshoot of that discussion, we're going to be describing today how theories can be tested literally in this room to determine if they're right or not. And you'll be testing hypotheses and theories all of your life, whether you're in business, science, the humanities, whatever it is you do in your life, you'll be asking, am I right or am I wrong? So let me start today with some announcements as usual. I'll remind you that there's homework due tomorrow, and it's all on Chapter 3. So if you haven't had a chance, find a couple of hours quiet, away from the frenetic pace of life, and read Chapter 3. It's very easy reading. There's a couple of issues that I'll highlight in my lecture that take a little more thinking, and then you should be able to do the homework. As usual, it's all in Mastering Astronomy online, and it's due tomorrow at 6 p.m. There will be a few pop quiz questions in today's lecture, so please get your colored pieces of paper out. And maybe if you don't have one, could you raise your hand now? And do the GSIs have, there's a few people that don't have colored pieces of paper. Now's a good time to get one before I get to my questions. While we're doing that, let me remind you that in the lecture on Tuesday, I described an observing project, the first of what I think will be 3 observing projects during the semester. And I'm just showing a shorthand version of it here, but the basic idea is really quite amazing. You yourself should be able to detect the planet Mars and the planet Saturn with your naked eye. Find them in the night sky, and also find the star that they are near, Antares. And if you're observant, you should be able to see these 3, Saturn, Mars, and Antares, just after sunset. And I can tell you that they are indeed only 10 or 15 degrees of angle above the horizon, so you'll have to look right after sunset. Well, wait till it gets dark, maybe 20 or 30 minutes after sunset. Look to the west, a little to the left is south of west, and there you should be able to see those 3 dots of light, Saturn, Mars, and Antares. It takes a little practice, by the way. I myself have to make sure that you get a vantage point away from buildings, trees, other tall objects that would block your view, because these 3 dots of light are only, like I say, 10 or 15 degrees above the horizon. And if you wait too long, if you wait until 9:30 p.m., of course they are setting in the west as the Earth rotates in the other direction toward the east. So you'll want to time your observation. Let me give you one more hint about this observing project. You're supposed to make 3 observations spaced somehow over the next 3 weeks. And I'll give you a little clue that, of course, some of the evenings, the clouds move in from the Pacific. The marine layer moves in, covers the sky. You can't see these 3 dots of light. So I recommend strongly that when you see a clear day come along, and today seems pretty clear to me, you should try to set your alarm clock, so to speak, and make sure you go out and look a few minutes after sunset, 20 minutes after sunset, and catch this when it's clear, because you may find yourself a week from now hoping to see them, but it's cloudy and you have no chance at all. So make sure that you take a good, get a good opportunity to look whenever you can. I'll give you one other little hint. It's due October 2nd, and I mentioned that you should get 3 observations between the 9th and the 30th. I can tell you that I'm hoping that you actually do see the motion of Mars, but Mars is moving relatively slowly, of course. It's not zipping along. So it's very valuable to make sure that you get at least 1 observation late in that 3-week period. In other words, near September 28th, 29th, or 30th, somewhere in there. Even if you extend over to October 1st, I don't mind. But it's good to get one of the observations as late as possible, because that gives Mars a chance to have moved enough so that you would be able to detect that motion. So in other words, bottom line, try to observe Mars as soon as you can in the next few nights, and try to get at least 1 of your observations as late as you can, and then 1 in the middle. And by the way, if you're a good scientist, why not get 2 or 3 observations in between so that you can see your own consistency of your measurements? Do your measurements seem to agree with each other as you place Saturn, Mars, and Antares? Okay? By the way, as a show of hands, how many of you have already seen the 3 dots? Did you already look last night or the night before? There's about 10 or 15 people. Definitely try to do it in the next 2 or 3 days. The weather, this warm weather we're having, means the sky is relatively clear. Okay, now a little history. I mentioned last time that Copernicus really made a strong argument that the sun was at the center of the solar system, not the Earth. And not everybody believed him. The Greeks certainly had reason to imagine the sun was at the center, but it was so obvious the Earth was at the center that the Greeks put it there, except for a few brilliant ones. And then Copernicus realized that a much simpler model of the solar system can be obtained by imagining that it's the planets that go around the sun, not the planets and the sun going around the Earth. One of the key observations that led to this discovery and to a refinement of it that I'm going to get to in a minute, one of the key issues was this motion of Mars. And you may remember last time I emphasized that Mars normally moves against the background stars night after night, moving a little bit in its orbit around the sun, we now know. But every once in a while, for about 6 weeks or 8 weeks, Mars stops and goes backwards, retrograde motion, and then goes forward again. And I mentioned to you that the reason for this is that the Earth is passing Mars on the inside track, and as we on the Earth pass Mars, we leave Mars behind, making Mars appear to go backwards. But it's really only the Earth going faster in its orbit. Well, the guy who made the best measurements of this retrograde motion and the motion of Mars in general was this guy, Tycho Brahe. You've probably never heard of him, but he was an amazing character and certainly the best observational astronomer of his time. He observed the position of Mars night after night after night for decades. And his measurements of the position of Mars were so renowned and respected that he got funding from the King of Denmark, as you see here. They even gave him his own island just outside Copenhagen. It's in the waters north of Denmark, between Denmark and Sweden. And you can even go and visit this island that was given to Tycho Brahe for his observatory. They didn't have telescopes, but he had a long tube, and he could point it right at Mars and measure where Mars was. Well, Tycho Brahe's data on Mars were renowned and precious. And the question is, who gets to analyze his data? The data being the position of Mars on every single night. Well, several astronomers wanted the data. One of them was a guy named Johannes Kepler. I mentioned him briefly last time. We're going to talk about him again. And another one was this Frank Tenagle. And there were other astronomers that wanted Tycho Brahe's data. They were desperate for his data because they thought they could come up with a new theory, a model of the solar system using his data. These other astronomers were so desperate for his data that when Tycho Brahe died, there was a clear suggestion that he had been murdered. And people thought that he had been murdered by one of those two astronomers that wanted his data, that they killed him and they stole his data. And you can see a whole article about it here. Tycho Brahe devoted his life to science, charting the positions of celestial objects. And there were lingering questions about his death in 1601 at the age of 54. And people continued to be worried about his having been murdered for centuries until finally some people in Denmark decided to dig up the body in his gravesite to see if he was poisoned. So in fact, this happened. In 2010, they checked, they dug up, there's Tycho Brahe. Not bad for his age. And they examined his body to see if it had mercury poisoning. That was the preferred murder technique of the day. And they obviously nowadays can check, as they did a few years ago, to see if there was mercury in his body. And when they checked, they didn't find any. And you can read all of this. I'll put it online. They were looking for traces of mercury in the hairs from his beard, and they didn't find it. There were some other possible causes of death. They thought maybe his bladder had exploded and so on. You read about these crazy things here. So the idea that Kepler had killed Brahe, or maybe some other astronomer had killed Brahe, has never been proven, but you can see how precious astronomical data can be, that people get quite worked up into a frenzy about it. Well, Kepler did get Tycho Brahe's data and began analyzing it theoretically, asking the following question. Is it true that the planets go around the sun, based on Tycho Brahe's data, and are the orbits of the planets around the sun truly circles, as Copernicus had thought? And you can see what I say here. Assuming a circular orbit for Mars, Kepler could not match Brahe's precise measurement of the position of Mars. There was always a tiny difference, 8 arc minutes of angle between where Mars was and where Mars should have been if it was on a circular orbit. And so this discrepancy of 1/10 of a degree angle is pretty large. You could point to Mars being there, but it should have been there, 1/10 of a degree. So Kepler had no choice. He had to abandon the theory that the planets go around the sun in circular motion. Now, at this stage, Kepler could have gone the whole way and said, well, let's throw out the whole theory that planets go around the sun. But Kepler was smart enough to realize that that theory was too successful. The heliocentric model had too much going for it. And so he did something that's a hallmark of modern science. Instead of throwing out the entire theory that planets go around the sun, he only threw out the part that they were going in circular orbits. And he asked himself the question, could the planets be going around the sun in a shape, an orbital shape that's not a circle? And eventually, by trial and error, he came up with the guess that maybe the orbits are shaped in an ellipse, the mathematical formula that you again learned, as I mentioned, back in 9th or 10th grade. And here is the idea that is, it turns out, correct. You have the sun, a planet, and it goes around in this, you might say, egg-shaped orbit. It goes faster when it's close to the sun and slower out here, sort of like that. I'll show you this in a few minutes. And Kepler worked out that the planet Mars in particular must be going in an elliptical orbit, an ellipse, not a circle. That idea has been tested many, many times, and it's absolutely true. And it turns out it's not just Mars, but all of the planets go around the sun in orbits that are shaped like an ellipse with a different amount of ellipticity, as we'll discuss. And you may remember from 9th grade or 10th grade geometry that an ellipse has two foci. There's one focus at one end and another focus at another end, here and here. And the sun, it turns out, is located at one of the two foci, as Kepler found it to be. And all of the planets, including the Earth, go around the sun not in circular orbits, but elliptical, albeit nearly circular orbits. So let me now remind you of something that I started to talk about last time, which is how one describes an ellipse. And I'll remind you that you can vary the ellipticity in a mathematical sense. So here is, it's kind of faint to see. I don't know if you can turn the lights down a little bit in the auditorium, then I think they might be able to see the ellipse a little better. Anyway, here's the red ellipse right around there. And I can change the eccentricity of the orbit. I can make it larger, or I'm hoping I could make it larger. There. That's better. Now you can see the ellipse better too. So I can make the ellipticity larger. High eccentricity means a flattened, more and more flattened ellipse. In the limit where the eccentricity is 1, the ellipse is just a straight line. And in the extreme case where the eccentricity is 0, the shape is indeed a circle. A circle is a special case of an ellipse. There's another parameter. Oh, I think last time I moved the planet around like that. Like so. There's another parameter that describes an ellipse, which is its size. And we describe the size of an ellipse by not the length of the long axis from there to there, but half that long axis, the semi-major axis. And we can vary the semi-major axis down here. There's a big ellipse that you see. I'll make it smaller. And this is just a measure of the distance between the center and the longest distance away from the center, from there to there. That's the semi-major axis. We usually use the letter A to represent that distance. So you can characterize the size and the shape of an ellipse by just those two parameters, the semi-major axis and the eccentricity. Okay? Good. Kepler's first law, I should have mentioned it, as it's called, is simply that all of the planets go around the sun in elliptical shapes, shapes that are ellipses. That's the first law of Kepler, Kepler's first law. The second law of Kepler is something I also mentioned briefly last time, that the speed of a planet changes as it goes around the sun. When the planet is close to the sun, it goes fast. And when the planet is far from the sun, it goes slower. And it's predictable. And it's predictable in a very precise mathematical way. I'm going to describe it to you here. If you draw a line from the planet to the sun, that line sweeps out an area. Like here's my arm, I can sweep out a certain sort of triangular area. The amount of area swept out is an equal amount of area per second. Every second, or every minute, whichever you prefer, the line from the planet to the sun sweeps out a nearly triangular area that's the same amount of area every second. And so when the planet is close to the sun, in order for it to sweep out its requisite amount of area per second, it has to go very fast to make the base of the triangle quite long. And so here's a demo of this. So here's an ellipse with some eccentricity of about, 0.5. And I hope I can get this to go. Let's see. Oh yeah, I'm going to hit begin. So this makes it bigger and smaller, but I don't really want to do that. So now I'm going to show you the motion of the planet as it goes around the sun, and you'll see how its speed is predictable in the fact that it sweeps out equal areas per minute. Kepler's second law. And by the way, asteroids and comets also obey Kepler's second law. If you want, you can watch the speed up here. And let's make the eccentricity a little larger, a little higher. Ready? Go. Goes very slowly at the most distant point from the sun. And then it goes faster. Of course, let me foreshadow the lecture about 10 minutes from now. We'll talk about how it is that gravity, the gravitational attraction of the planet to the sun, is what holds the planet in and dictates this behavior. And you can almost see the planet falling into the sun or trying to fall by gravity, but it has a little bit of sideways motion that allows the planet to miss the sun, and nonetheless it is falling by the gravitational attraction of the sun to the planet. And so in a way you can begin foreshadowing our knowledge of gravity by watching the planets, and that's exactly what Isaac Newton did, as I'll mention in a few minutes. Okay, one more perihelion, as they call it. Good. So there's a third Kepler law, and this is the most beautiful of the three of them. The first two were pretty good. Planets move in ellipses, profound, not circles. Planets sweep out equal areas per minute. That's cool. But there's a third law that's even more unbelievable, and it's this one here, Kepler's third law. If you write the orbital period of a planet, the time it takes to go around, as capital P, and you write this semi-major axis, the distance from the center of the ellipse to the edge of the ellipse, as capital A, sorry, lowercase a, it turns out, who knew, that for all of the planets in the solar system, and by the way, the asteroids and the comets that go around the sun as well, for all of them, if you take the period and square it, it turns out to be exactly equal to the semi-major axis cubed. P squared equals A cubed. I don't know how you would ever guess such a thing. Johannes Kepler, being sort of a mathematical and spiritual geek, tried all sorts of different equations that might relate the orbital period to the distance of a planet from the sun. And lo and behold, he just hit on this equation, which works. P squared equals A cubed. You can use this to take the orbital period and calculate the semi-major axis, which is essentially the average distance from the sun to the planet. So here's a quiz question that makes use of this Kepler's third law, P squared equals A cubed, and now you're going to have to do a little bit of algebra. You might want to do it on a piece of paper. I'm going to give you about 30 seconds to answer this question. Suppose there's an asteroid that orbits the sun, and the average distance, in other words, the semi-major axis, from the sun to the planet is 4 astronomical units, 4 times the distance from the Earth to the sun, 4 AUs, 4 Earth-sun distances. What is the orbital period? Take a few seconds to think about this. Given the distance of a planet from the sun, what is the orbital period? All right, go ahead and show me your answers. I can tell you that I see lots of letter B's and D's, mostly B's and D's, a few C's, some people that are flipping between A and C. Well, here's how I do the calculation. Let me try to do it in my head. I'll speak out loud as I'm thinking. I don't actually know the answer. So if the semi-major axis is 4 Earth-sun distances, that's the distance from the planet to the sun, Kepler's third law says take P squared is equal to A cubed. Well, I'm given A. If I cube 4, 4 times 4 is 16, times 4 again, 4 times 16, 4 times 10 is 40, but there's an extra 6. 4 times 6 is 24, 24 plus 40, 64. Okay, 4 cubed is 64. I'm a little slow. Bear with me. 64. Now that's the right-hand side. If the right-hand side is 64, then P squared is 64. So P must be a number which, when squared, gives you 64. And I think that's 8. 8. Oh, what are the units? 8 days? Oh yeah, years. Why? Because I didn't emphasize this, but this law only works if P is measured in years and A is measured in Earth-Sun distances, AUs. So using those units, P and A, then this equation is correct. And now we get 4 cubed is 64. The square root of 64 is 8. So I guess the answer is B, but let's find out. Yes, that's right. And you can see I kind of worked it out again here. So you can use Kepler's third law if you know one quantity, like the orbital period of something, you can calculate the semi-major axis and vice versa. Let me foreshadow the next couple of chapters later in the semester. It will turn out that Kepler's third law also works not just within our solar system, but for other planetary systems around other stars. But we'll need to modify Kepler's third law a little bit in order for it to work properly for another star. But Kepler's third law will make a comeback for other planetary systems. Now, of course, you can check Kepler's third law. You don't have to take my word for it or even Kepler's word for it. You can look up the distance from the planet to the sun for all of the planets. There they are in AUs. You can look up the orbital period of the planets. These can be easily observed by the naked eye. Wait for the planet to go around the sun once. It's not so easy to get the distance from the sun to a planet, but that can be measured also. And you can check, is it true that the cube of that number equals the square of this number when written in years? And sure enough, they're exactly equal. They're equal to 8 significant digits. Okay? Now, why does this happen? And by the way, let's back up. Why do any of Kepler's laws work? Why do the planets orbit the sun in ellipses? Why does a planet sweep out equal areas in equal times, going fast when it's near the sun and slow when it's far away? And what about this p squared equals a cubed thing? These are observed relationships, geometrical and algebraic, that Kepler discovered by just looking at Tycho Brahe's data. But there must be a reason the universe just isn't doing things for the heck of it. And I've already mentioned what underlies these laws that nobody knew about at the time. The underlying, very simple and powerful reason for all of those relationships, the Kepler's 3 laws, has to do with gravity. Gravity is the force that governs the motions of objects in the universe, whether they are planets, asteroids, comets, stars, or whole galaxies. It's gravity that governs the accelerations, the trajectories of the objects. And so let's talk a little bit about gravity. Was not known to Brahe, Copernicus, or Kepler, but it was obvious to people in that era, the late 1600s, that the motions of the planets governed by Kepler's laws must have a reason, and there must be some attractive force that holds the planets to the sun. And people even guessed that there must be some relationship between the gravitational force and how far away the planet is from the sun. What is that algebraic equation? Is the force equal to 1 over the distance, 1 over the distance squared, 1 over the distance cubed, 1 over the distance to the 4th power? Is there something about the masses of the planets or some other aspect? What is it that makes up this gravitational force? This was such a compelling question that a British member of the royalty issued a small prize of 40 shillings for the first person who could figure out what kind of a law of gravity would explain, in one fell swoop, explain all of Kepler's laws that seem utterly different from each other. And luckily, Edmund Halley, who was intimately aware of the comets' motions that were elliptical, talked with Isaac Newton in Cambridge, England, and gave Newton the impetus to see if he could figure it out. And Newton did. He tried to figure out what that law of gravity must be to explain Kepler's laws. And I'll just mention as a parenthetical background that Isaac Newton realized that there must be some physical laws that pertain everywhere, not just out in the universe governing our solar system, but perhaps here on the Earth. And all of you know the apocryphal story about Isaac Newton standing or sitting under an apple tree and having an apple plunk him on the head, and he looks up and sees the moon, and he starts thinking maybe what held that apple to the Earth is the same thing that holds the moon to the Earth, namely gravity. And you could extend that out to the planets and the sun. And so Newton started thinking about how laws of science might pertain not just here on the Earth, but everywhere. Quite profound. Why should it be? He discovered laws of motion, forces, accelerations, speeds, how objects move due to those forces, and in particular, the force of gravity, which I'll show in a second. He also did experiments with light. He was the first person to invent a reflecting telescope. And he ran into trouble trying to understand the motion of the planets due to gravity because there was no mathematics that gave him the tools to work with gravity. So along the way, as a side project, he invented calculus. It's something to do on the side while you're doing your important work. So he invented calculus that many of you know from having taken it in high school, or maybe you're taking it now. All of it as a mathematical tool to understand the motions of the planets. And here's the law of gravity. All of you have seen it before, but let me now tune it up for you. If you have two massive objects, let's call the mass number 1 and give it an amount of mass m sub 1, another massive object with a mass m sub 2. These are just symbols representing how many kilograms are actually in each one of those objects. And if you then move those two masses a certain distance apart, let's call that distance little d, then there's a formula that you can demonstrate empirically, that is to say experimentally, between the force that each of these masses experiences. I'll say that again. Each of the masses experiences an attractive force to each other, and the amount of that attractive force shown by the arrows is given by the mass of the first object times the mass of the second object divided by the distance squared. And then there's a constant of proportionality that makes the units work, capital G, called the gravitational constant. No one knows where it comes from, but you can measure it by measuring forces, masses, and distances and asking what is the proportionality constant. We call it this constant of nature is the gravitational constant, capital G. And so this is a very beautiful law of gravity. I say beautiful because there's some symmetry to this equation. Notice that m1 and m2 both appear in the numerator equally. It's not as if m1 is more important than m2. Moreover, the force here represents the force both on m1 toward m2, and it's the force on m2 toward m1. So there's just one force acting on both masses in opposite directions, making it attractive. And the most elegant part of the law of gravity is that the gravitational force gets weaker and weaker and weaker as you move the two masses farther and farther apart, as the distance squared. If you have two masses a certain distance apart, and you double the distance, the gravitational attractive force is then less by a factor of not 2, but 4, 2 squared. So if you take two masses and you triple their distance apart, the gravitational attractive force is now 9 times less, 1/9 of what it was, because of that d squared term. Okay? That's the law of gravity. It's an extraordinarily powerful equation and ridiculously simple. And I can tell you that that equation nearly by itself explains Kepler's 3 laws. And this is, again, a hallmark of science. If you've really learned something about nature and you have an explanation and a theory that's more sophisticated than just a collection of data, that more sophisticated theory should be simpler than the collection of data that the theory explains. Otherwise, why not just keep all the data hanging around? This is a very simple little formula that actually from it you can derive Kepler's 3rd law on the back of an envelope. So that leads to a quiz question. Ready? This is an easy one, I admit, but I hope you get it. Is the force the Earth exerts on you larger, smaller, or the same as the force you exert on the Earth? Are you pulling on the Earth stronger or less strong than the Earth is pulling on you? You can show me your answers if you want. This is a trick question. I see a lot of A's and a lot of C's. It's a trick question because, I mean, come on, the Earth is enormous. Clearly it's pulling on me. My feet are planted on the ground because I'm pulled downward by the enormous force of gravity exerted on me by the enormous planet Earth. Now, am I, with my little body, pulling on the planet Earth by the same amount of force? Doesn't seem very likely. But in fact, it's true. The 2 masses, the Earth and my body, we both have masses. The amount of force acting in either direction is the same. So the Earth and I exert equal and opposite forces on each other. Why do I say opposite? The gravity from the Earth is pulling me down. My body is gravitationally pulling the Earth toward me. And you should be really uncomfortable right now. Because if you're really believing what I'm saying, I mean, come on, my little body here is pulling on the Earth with the same force that the Earth is pulling on me downward? How can my little body do that? And by the way, if I'm pulling on the Earth so hard, why doesn't the Earth fall toward me? Why doesn't the Earth just fall toward me, just like I fall toward it? And the answer, in a nutshell, is that the Earth is falling toward me, and by the way, the rest of you, but the Earth is so massive that it resists the acceleration toward each of our bodies by virtue of the enormous amount of mass that would have to get moved, accelerated toward my body or your body. So I'm pulling on the Earth gravitationally, but the Earth is just so huge, it hardly budges. It's like if you try to push on a building or push on a truck on wheels. You can try to push a truck. It's just so massive it hardly budges. I'm yanking on the Earth, but it hardly budges because of its mass. Okay? So that was a little quiz on gravity, and you'll get some more ideas about gravity in your homework this week. By the way, one historical footnote that I'm going to spend only a small amount of time on, but I'm heartbroken, and that is there was one more historical character that I haven't mentioned. Galileo Galilei lived in Italy, and while Copernicus was not successful foisting the heliocentric model on the world, and even Kepler didn't win over very many converts, Galileo did. And he did because he invented the telescope for use in the night sky. And among the many discoveries Galileo made was that the planet Venus, as you see here, occasionally was seen in a gibbous and even full phase. how could the planet Venus ever be a full moon if Venus was going in an epicycle in its orbit around the Earth? Remember the epicycles, those crazy little tiny orbits as planets go around the Earth in a geocentric model. In this model, check it out. Venus will loop-de-loop, but the sun will always illuminate Venus from the back side. You might see a crescent Venus here and here, but you'll never see a gibbous or a full Venus because it's the backside of Venus that's being illuminated by the sun if you adopt the geocentric model. And Galileo, with his telescope, for the first time ever, looked up at Venus and occasionally saw that it was gibbous and even full, and that proved geometrically that Venus must go behind the sun so that it could be fully illuminated, the hemisphere that we see. And that lent very strong support, as you can imagine, to the so-called heliocentric, sun-centered model of the solar system. And there were other observations Galileo made that really supported strongly the sun-centric, heliocentric model. So Galileo was a cool dude, and what's profound about it is that in a way he was testing a model. Earth-centered versus sun-centered. Which is right? He employed the scientific method to distinguish. There was a question. Do the planets go around the sun or the Earth? You have a hypothesis. Maybe the planets go around the sun, or maybe they go around the Earth. Those are perfectly good hypotheses. You can have an explanation for various phenomena that you see. The predictions are clear. In the case that I just mentioned, if the geocentric model's right and epicycles are right, Venus should never be gibbous or full. That's a prediction. You test it by pointing your telescope, doing the experiment, and then look at the result from that experiment and ask, did the result agree with or disagree with the prediction from the model? Notice the tension, the conflict. You have an idea, a hypothesis, a theory. You predict something will result from that theory. By the way, what's the good of an idea if it doesn't predict something that you didn't already know? It's not very helpful to have a theory about something unless it allows you to extrapolate, extend your knowledge beyond what you've already experienced. So a good theory does that. And then the question is, when you do an experiment, did the results agree with the prediction or disagree? And then depending on that, you may want to reject the theory entirely or modify the theory. As I was mentioning a few moments ago, you don't throw out the heliocentric model just because the planets are not going in circles. You modify the theory and let the planets be in elliptical motion. So this is a great example of the scientific method. And when you've decided there's something wrong with your theory, go back up and change it or make a new one. And you loop around over and over in science, perhaps taking weeks or months or years or even centuries. Every time an experiment disagrees with a prediction, you have to ask, does this weaken the theory, weaken the hypothesis so much that we have to throw it out? A good example is the theory of evolution, Darwin's theory of evolution. There are thousands, tens of thousands of experiments done by biologists for the last 100 years. And those experiments always confirm Darwinian evolution, time and time again. And if one of them didn't, we'd have to throw out Darwinian evolution. But after 10,000 experiments get 10,000 experiments support the theory of evolution, you don't have any choice but to bet with your money, if you would, that the next experiment you do will also obey Darwinian evolution like the last 10,000 experiments you did. The law of gravity is the same. And notice, by the way, we often call it a theory of gravity, the theory of gravity. Yeah, it's a theory, but, you're not going to throw out the law of gravity anytime soon. It's been tested too many times. And by the way, when you do an experiment, you as a human being, I'm sorry to report, have biases. You're not always honest. You want to be honest, but you maybe favor one hypothesis over another. You do your experiment, maybe you only accept the results that favor your hypothesis, and you give less importance or weight to the results that seem to disagree with your theory. So we humans can often be flawed as agents of the experimental process, and that's why it's very important that different people do experiments, because different people come with different biases, and hopefully you'll be able to sort out what the truth is by watching the results come from different people. So, to summarize, science always looks for an explanation of the observations that you take, and those explanations should rely on natural causes, ideas that you can see around you of forces and velocities and temperatures and so on. Science progresses, as I've said, through constructing theories or models that explain the observations. And if the observations end up disagreeing, you have to throw out the model. If you have multiple models or multiple theories, why not adopt the simplest one, the simplest model first? That's called Occam's razor. Adopt the simplest model until it doesn't work, or if it doesn't work. But if it does, why not stay with it? And all theories, all hypotheses, if they're of any use at all, think of any idea you have about how nature works, how the universe works. If that idea doesn't make a prediction, it's not very useful. You might have an idea that, let me make one up here off the top of my head, that angels that are invisible in this room are going to govern the grade that you get at the end of the semester. The angels actually determine what grade you get. It's a pretty good hypothesis, but how can you test it? I mean, how would you know at the end of the semester whether the angels caused you to get the grade that you got? So theories are fine. Maybe there are angels floating around this room, but they're not very that theory isn't very useful if you can't say one way or the other, if you can't anticipate the future based on it. Okay. I'll introduce two words, and then I'm going to show you something completely different. A good word is pseudoscience. There are a lot of people in your lives who show up on TV or maybe at a podium somewhere, maybe even some of your professors, who think they're telling you the truth, but they're actually just giving you their biased beliefs. So you really should adopt the point of view that you shouldn't really believe anybody unless you see some supporting evidence. If the President of the United States says something, how do you know it's true? If a business leader, the owner of a company tells you, buy my product because it's the best, how do you know that's true? If a religious leader tells you something is true, how do you know? So you should always really adopt the idea that beliefs that people have are often wrong, and it's really better to ask, how do we know? What's the evidence? Because we're wrong more often than we're right, and we have biases. And then there's something called non-science, which is apparent truths that just come because you believe. And, you know, believing is fine. We should all respect each other's beliefs, but it doesn't mean that it's actually true. And that brings me to a great theory in astronomy called astrology. All of you have heard about astrology. What's the difference between astrology and astronomy? Well, the answer is lots and lots of math. But is astrology a good theory? I mean, does it say something about our lives? And I'll remind you, the idea of astrology is that the positions of the sun, moon, the planets determine your personality and determines what kind of a day you're going to have. You read a horoscope and you read it in the newspaper or in a magazine or online, and it tells you what kind of interpersonal relations you're having with your friends or your, maybe your lovers or your professors or something like that. So astrology is a good theory. You can test it. They make predictions. You should be able to compare the prediction that shows up in the horoscope, compare it to the real world. I have no beef with a great theory that makes predictions that is transparent. And so the theory is that the positions of the planets, moon, and the sun at the time of your birth, i.e. what astrological sign you have, determines your personality and your future day after day after day. You can learn a lot about astrology. It's a very well-studied scientific pursuit, you might say. You can read books from hundreds of books on astrology. Lots of people will tell you if you go out on Telegraph Ave, they'll read your horoscope and tell you what your day is going to be like. So here's some books on Amazon. There's some really great ones, Ruling Planets. The planets and the positions of the planets at the instant you were born determines the rest of your life. Pretty good theory. And you all have a sign. I think all of you know your astrological sign. You're one of these signs. By the way, these astrological signs, of course, are constellations in the night sky where the sun was 3,000 years ago. During the daytime during these months. So if you're a Taurus, that's because the sun between April 19th and May 19th, the sun was in front of the constellation Taurus. And so it is with all the rest of these. I think all of you know your astrological sign, right? Everybody knows your sign because you can't live without knowing your astrological sign. I mean, you could run into a mountain or have a truck hit you or something terrible. And so just to give you a clue about your life, all of you, since I do want to take care of all of you, I've brought your astrological horoscope today so you can find out about yourself. Here it is, San Francisco Chronicle, a world-renowned source of astrological information. Today, September 11th, 2014, this is today's Chronicle. And please, if you have your laptops open, don't look it up online. That's not fair right now, because I'm going to do a little test with this. So please don't go over to sfgate.astrology or whatever the heck it is. And here are the 12 astrological forecasts for your life. And I'd like to do a test of astrology. It's a scientific pursuit. Let's test it right here in this room right now. And the way we should do that is the following. I want all of you to get out a little piece of paper. You could use the back side of your four-colored piece of paper, just some little piece of paper. I even want the GSIs to do it. Any little scrap of paper and a pen. I hope you have a pen somewhere, because I want you to write down on that piece of paper right now the sign of the zodiac that you are. Okay? Just write down Pisces or Libra or Scorpio or whatever you want, just so you have it right there in front of you. Now, I'm going to show you these horoscopes here, the 12 of them, but I'm not telling you the astrological sign they correspond to. So I'm going to show you them again, but I want you to write down which of those 12 is you. So which of the 12 horoscopes best describes your day? By the way, it's 6 p.m. right now, so most of the day has gone by. These horoscope predictions that I'm going to show you again represent your day today. It's already happened. Surely you know what happened to you today, and you should be able to compare your astrological horoscope as dictated in the Chronicle against your actual day and recognize yourself. in those things. And then when you do so, write down that number. So here they are again. And by the way, the idea, just to remind you, here's where we're heading. If astrology as a theory is true, you're going to recognize which of the 12 horoscope predictions is you. If the theory of astrology is not true, you're just going to choose one of the 12 horoscope predictions at random. So that's the basic idea. And now let's do it. This is going to take a few minutes. I'm going to read all 12 of these out loud. And when you hear one that seems like you, write down that number. Ready? Prediction number 1. You win everybody's stamp of approval except one. Don't fixate on it. This person did it to mess with your head. If that sounds like your life, write down number 1 on the piece of paper. Okay, number 2. Coworkers praise you for something you didn't do. What's the harm in letting them believe what they want? You could use the good press. That sounds like you. Write down 2 on your piece of paper. Number 3. People don't know what they want, which is why they keep changing the rules and expectations. Do yourself a favor and stop trying to make things better. Pretty good one. That sounds like you. Write down 3. Number 4. One of these is you, by the way, so. Remember how you said you would never be friends again? It's amazing what time and hindsight can do to restore what was lost. Write down 4 if that sounds. Number 5, expect good news regarding a sale, loan, or some kind of funding. Sounds like money from mom and dad. The road to financial recovery is arduous, but you are making progress. Okay? Write down a 5 if that sounds like you. 6, certain conditions could impair or benefit you in ways you hadn't considered before. Only a careful examination will tell you which is which. Write down 6 if that's you. Number 7, why are you expecting to put up with others' shortcomings, but you're immediately taken to task when you do something wrong? Answer, you're the better person. Okay, I know everybody thinks they're number 7. I know. Number 8, today's Sun/Saturn sextile will help you identify what's important and to offload those commitments and obligations that have outlived their purpose. It's number 8. Number 9, listen to what a coworker says. His or her approach may be rough, but his criticisms are fair. Number 10, your looming deadlines, that sounds relevant already. Your looming deadlines will always be there, but the people who matter might not be. It would be a good idea to make room in your busy schedule for them. That's number 10. Here's number 11. This is a good time to explore refinancing, reworking your financial portfolio, and or consolidating investments. You don't want to sit on your assets. Those astrological folks, they know stuff. And then number 12, a critic becomes an ardent supporter. It just goes to show that you can never judge a curmudgeon by his scowl. That's number 12. Okay, now all of you, give it a little bit of thought, but you have to write down a number. Everybody has to write down one of those 12 numbers. After all, one of them must be you. I'll give you about 15 seconds to write down one, and then we're going to see who's who. Okay, do you all have a number written down? All right. So we're going to test astrology and see if you guessed correctly which one of these is you. Here they are again. And what we're going to do here is one by one see if you got it right. So let me ask, if you chose number 1 as your sign here, stamp of approval, so on, please stand up. If you chose number 1. I see 3, 4 people standing up. Okay, now I'm going to reveal which of the astrological signs number 1 is. And if you're right, stay standing up. And if you're wrong, sit down. You got it right. 1 person out of 4 got it right. That's pretty good. And by the way, when is your birthday?
September 22nd.
Cool. All right, now if you chose number 2, stand up. Anybody? Oh man, there's going to be a lot of them coming down the pike. Oh, let's skip number 2. Oh, you're number 2? All right, here's number 2. No? All right, stand up if you chose number 3. Changing rules and expectations. A lot of number 3s. I see about, there's about 15 people standing up. Here's what number 3 was. Stay standing up if this is you. Ready? Sagittarius. Is that you? 1 out of 15 got it right. But 14 out of 15 got it wrong. All right, number 4, stand up if you chose number 4. Anyone choose number 4? 1 person? 2 people? 3 people? Brave, you're brave. Okay, stay standing up if this was you. Cancer. Yeah, that's you? Wow, that's pretty good. 1 out of 3 that time. All right. Stand up if you chose number 5. Yeah. Okay, 1, 2, 3, 4, 5, 6. There's maybe another 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 13 or 14 people. Okay, stay standing up if you were Leo. You're Leo? 1 out of 15 got that right. By the way, you realize that there's about a 1 out of 12 chance you'll get it right if you did this blindfolded. Okay, stand up if you chose number 6. Okay, I see about 30 people standing up. And stay standing up if you chose Virgo. I see 1 person, 2 people standing up. That's 2 out of 30. That's not too bad. Very good. All right, you ready for number 7? Lucky number 7. Stand up if you chose number 7. I see 1, 2, 3, 4, 5, 6. And stay standing up if you're Aries. You're Aries? Hey, that's because you read the horoscope in the morning. All right, 1 out of 7 got that right. How about number 8? Stand up if you chose number 8. There's still a lot of you that haven't stood up yet, I think. I see about maybe 10 or 12 people standing up. Okay, stay standing up if you were, Taurus. Taurus is number 8. You're Taurus? Hey, that's pretty good. 2 people got that one right. 2 out of like 10 or something. That's not bad. All right, stand up if you chose number 9. Number 9. 1, 2, 3, 4, 5 people maybe. And stay standing up if you if you're Gemini. You're Gemini? 1 out of 5 got that one right. Not too bad. Number 10. Stand up if you chose number 10. Yes, it's very popular. There's about 80 people standing up. And now stay standing up if you're Capricorn. Hey, that's pretty good. 1, 2, 3, 4, 5 people, and 6 even. 6 people out of 80 got that one right. And we're almost done. Stand up if you chose number 11. Number 11. 1, 2, 3, 4 people maybe. And stay standing up if you're Aquarius. You're Aquarius? 1 out of 4, not bad. And then the last astrological sign. Stand up if you chose number 12. Of course, by this point, you already know whether you made it or not. But stand up if, be honest, stand up if you chose 12. Nobody chose 12, and not even her. And that one was Pisces, as you might have been able to guess. So now we can kind of summarize what's happened here. You got the idea that maybe 1 out of 10 or 1 out of 12 of you got it right, and the rest of you got it wrong. That's what you would have expected if you were blindfolded, if you didn't even read them at all. So really, the theory would have been considered true, the astrological theory, the theory of astrology would have been considered true if people could have indeed recognized the day that they're actually living. And you have to consider the theory dubious at best, if not indeed bogus, if people don't recognize their own horoscopes. And something like 1 out of 10 of you, you notice that I've done this before, got it right. And so that casts a lot of doubt. You might be casting horoscopes, but you should also be casting doubt on the veracity of astrology. It really doesn't tell you much about your day. And you should also be asking a plausibility question. Give me a break. Is it really true that the positions of the planets and the moons on the day that you're born govern what your days are going to be like, your emotions, your interpersonal relationships? So when you're testing a theory, there are 2 components. A theory must stand up to predictions, and you should be able to tell whether the prediction agrees with the actual observation. But theories should also be plausible. They should make some sense. Yeah, if they don't, maybe you don't rule it out right away. But there ought to be some thread of logic that connects the ideas of a theory to the predictions that it might make. And it seems, in my opinion, quite implausible that the position of Saturn or Uranus or Neptune, which, by the way, were not even known to the ancients when they concocted astrology, why should it be that these planets so far away would make a difference in your life day after day? After all, the gravitational force on you from Jupiter or Saturn is less than the gravitational force on you when you're born from the doctor that's standing next to you. You know, the position of the doctor should determine your astrological sign more than the planets. Or maybe, whether Boeing 747s are flying over your hospital when you're born. They have mass, they have a gravity. Maybe it's the positions of all of the commercial jet airliners in the United States that determine your astrological sign. These become more and more ludicrous. So you get the idea. It's really a wonderful thing to do in your lives, to doubt your beliefs, test your beliefs, and retain those that seem to work, and throw out the ones that don't. So I'll stop there. Good luck on your homework tomorrow.